Good morning, students. Now, orthogonality and least squares, right? This is the fourth unit. I'll wait for 2 minutes. I'm searching for pencil. Right. Inner product, length, and orthogonality. The inner product. Already we defined inner product. Inner product of two vectors. That means u dot v. U dot v can be written as u transpose v, and it is can be written as a1 b1 plus a2 b2 plus a3 b3 and so on an bn, right? Inner product of two vectors. You know how to find a product of two vectors, and these are the examples. And some properties are there. U dot v is equal to v dot u. That means inner product is commutative, right? Now distributive laws, right? U plus v, right distributive law, left distributive law, and scalar multiplication. And inner product of any vector is always greater than or equal to 0 if u is equal to 0, inner product is 0. Otherwise their dot product is always greater than or equal to 0. And length of a vector. Length of a vector is denoted by mod v, or you can say, norm v. Norm of v is equal to square root of v dot v, right? This can be written as this one. This is the definition of norm of a vector, or you can say length of a vector, right? Next one. There is one simple problem is there. Find the length of a vector. This one is done. Next, distance. Distance between two vectors is denoted by d of u comma v. It can be written as norm of u minus v, right? Definition is norm of u minus v. What this can be written as square root of u minus v dot u minus v, right? Now you know how to find the distance between two vectors. Next one is orthogonal vectors. Two vectors are said to be orthogonal if their dot product, inner product is equal to 0. And there is a one Pythagoras one formula is there. One theorem based on inner product. Okay. Next one. The definition of inner product. The vectors u and v in R power n are orthogonal to each other if u dot v is equal to 0. That is the definition of orthogonal. And Pythagoras theorem. Already we explained this one, right? Next, orthogonal complements. Orthogonal complement is a definition which is nothing but it is a collection of vectors. It is a collection of vectors in a vector space which are orthogonal to every vector in the subspace of R power n. Right? See here, suppose one R power n, let some V is a vector space is given to you. If you want, you can read this sentence. If a vector Z is orthogonal to every vector in the subspace of R power n, then Z is said to be orthogonal to W. Okay. The set of all vectors Z that are orthogonal to W called orthogonal complement of W, and it is denoted by W to the power of perpendicular symbol. W perp, which is read as W perp, or W to the power of perpendicular symbol. What is the definition of orthogonal complement? Now here R power is in a vector space, and W is a subspace of R power n. Okay. Now we have to collect. Suppose let Z be a vector in R power n, which is orthogonal to every vector in W. What is W? Subspace of R power n. Then we can say that Z is orthogonal to W. That's fine. Now we have to collect such vectors from R power n. Right? We have to collect the vectors from R power n, where R power is a vector space, which are orthogonal to every vector of W. What is W? Subspace of R power n. That collection of vectors which are orthogonal to every vector of W is called orthogonal complement. It is denoted by W to the power of perpendicular symbol. And one example is there. It's not necessary, right? And some properties are also there. See here. A vector x in orthogonal complement of W if and only if x is orthogonal to every vector in the set of that spans V. That is true, no? Orthogonal complement is a subspace of R power n. Orthogonal complement is a subspace of R power n. Now can you prove this one? Try to prove this one. W perpendicular is a subspace of R power n, where R power n is a vector space. No, what is the definition of subspace? When do you say that a set is said to be a subspace of vector space? It has to satisfy three properties. What are they? First one, zero vector in R power n is also in W or some set, right? Next, U minus V, internal composition and external composition. If those three properties are satisfied by the given set, then the given set is said to be a subspace of given vector space. Here you have to show that this W power perpendicular, that means orthogonal complement of W, we have to show that this is a subspace of R power n. That means we have to verify these three conditions. First of all, zero vector of R power n is also in this set. We have to prove that the zero vector of R power n is also in this set. How to prove that one? That is a question mark. Simple one. See, what is W complement? W complement contains those vectors of R power n only, right? We are collecting as per the definition of W power perpendicular, means this set contains the vectors from R power n only, which are orthogonal to every vector of W, no? Right? Now see, next one is we have to show that zero vector in R power n is also in W complement. Now see, you take one zero vector in R power n. Now 0 is a vector in R power n, whether this is orthogonal to every vector in W or not? Yes, because 0 dot any vector in W is equal to 0, no? The inner product of this vector 0 dot any vector in W, what will be the answer? 0 only. 0 dot u1 is equal to 0, 0 dot u2 is equal to 0, 0 dot u3 is equal to 0, right? That means 0 is a vector in R power n which is orthogonal to every vector in W. Therefore, we can collect this 0 vector in W complement. What is the definition of W complement? We have to collect those vectors from R power n which are orthogonal to every vector in W, right? Here, since 0 is a vector in R power n which is orthogonal to every vector in W, therefore we have to collect 0 belongs to W complement, right? Now what about internal and external complement? Try to solve those things. Next. There is another theorem. Let A be a n by n matrix. The orthogonal complement of row space of A is null space of A, and the orthogonal complement of column space of A is the null space of A transpose. Here in words is given here. In symbolic form, it is given in the next line. Right? This, please go through this theorem which is in your notebook. Right? It's a very easy one. Later I'll explain that theorem. Right? Now angles in R square and R cube. R square is a vector space, R cube is also a vector space. Now say U and V are any two vectors in a given vector space. The angle between U and V is denoted by, see, U dot V, inner product of U dot V is equal to norm U into norm V into cos theta, where theta is the angle between the given vectors. This is the formula you have to remember, right? The angle between two vectors is denoted by, right, theta, and it is given as U dot V is equal to norm U into norm V into cos theta. Okay, only one simple definition, there are no problems. We have done all those things now. Now I have already explained orthogonal set. Orthogonal set means, suppose S is a set is given to you which contains three vectors, say u1, u2, u3, right? Now, this set is said to be orthogonal set if every pair, each and every pair of these vectors are orthogonal. That means u1, u2 are orthogonal, u2, e3 are orthogonal, u3 and u1. Right? If all the pairs, each and every pair of those vectors are orthogonal, then the set is said to be an orthogonal set. Right? And I explained this theorem also. If yes, u1, u2 and orthogonal set, then it is linearly independent and it is form a basis, right? There it is there in your notebook. Now, see this theorem. Let u1, u2, up be an orthogonal basis for a subspace W of R power n. For each y in W, the weights in the linear combination y is equal to C1 u1 plus 1 C2 u2 plus 1 Cp up are given by Cj is equal to y dot uj by uj dot uj, where j running from 1 to p. This theorem we are going to explain. After this, one problem is there. Next important topic is orthogonal projection. This is very important topic, orthogonal projection. This topic is very important. Okay. After orthogonal projection, there is only one concept is there, that is Gram-Stitt orthonormalization theorem. See, Gram orthonormalization theorem. There are two important topics are there. We will discuss those topics in the next video. Now see. Now our notes. We have explained inner product, right? And the properties, length of a vector, or you can say name of a vector, right? Next, what is unit vector? Normalizing. Next, next one is find a unit vector in the same direction, right? Next, one example based on unit vector. Next one, W is a subspace of R1 spanned by some x. Find a unit vector Z such that is a basis for W. You know how to find the unit vector. Unit vector is nothing but u by norm u. Next one is distance. The definition of distance. Let u and b are any two vectors. The distance between two vectors is denoted by d of u comma v is equal to norm of u comma v. So norm of u minus v. And the example based on distance. Right? Another example. Orthogonal vectors. Definition. 0 vector is orthogonal to every vector in R power n. Right? Because the inner product of any vector with respect to 0 is always equal to 0. And Pythagoras theorem I have already explained. Converse of Pythagoras theorem. Orthogonal complement definition. Right? Next, W based on the theorem, right? Example and theorem. Please go through this theorem, right? It's a very easy one. Now, let u and v are vectors in R power and R cube, then angle between them is theta, then that is given by u dot v is equal to norm u into norm v into cos theta. Right? Orthogonal sets. This one also explained. Right? Next theorem, orthogonal set which is linearly independent. Next one, see this one. If u1, u tends on up is an orthogonal basis for a subspace W of R power n, for each y in W, the weights in the linear combination is given by this one. We have to show that Cj value is equal to this one. Cj is nothing but put j is equal to 1. What you will get? C1 is equal to y dot u1 by uj dot uj. J is equal to 1 now, u1 dot u1. Next C2 is equal to what you will get? Y dot u2 by u2 dot u2. C3 is equal to y into u3 by u3 dot u3. This is inner product, right? Now see, we are going to prove this one. It's a very easy one. What is the given data? R power n is a vector space, W is a subspace of R power n. Now u1 u2 and so on, up is an orthogonal basis for W. Orthogonal basis, it is a basis and also orthogonal, that's it. And y is a linear combination of these vectors, c1 u1 plus c2 u2 plus c3 u3 and so on plus cp up, where c's are scalars. Now from this equation we need to find all the scalars, right? Now from equation 1, both sides we are multiplying by u1. See, both sides we are post multiplying by u1. Okay, now y dot u1 is equal to, if you multiply inside c here, c1 u1 dot u1 you will get c2 e2 into u1. u2 dot u1 is what? 0, because this set is orthogonal. No, orthogonal means a set is said to be orthogonal if every pair of vectors, every pair of distinct vectors, actual word is, that means u1 dot u2 is equal to 0 or u2 dot u1 is equal to 0. u3 dot u1 is equal to 0 or u1 dot u3 is equal to 0. Similarly, up dot u1 is equal to 0 or u1 dot up is equal to 0. Since it is an orthogonal, rest of the terms becomes 0. c1 u1 dot u1, c1 into u1 dot u1. Now since u1 is not equal to 0, what is c1 value? If you transpose it to the right hand side, y dot u1 by u1 dot u1. Similarly, you can write c2, c3, c4, c5, right? We can generalize the case. You have to remember this one. Cj is equal to y dot uj by uj dot uj, right? That means if you put j is equal to 1, c1 value, j is equal to 2, c2 value will get, right? This is an important theorem. Please go through this theorem line by line. Okay, and one example is there. I'll explain this one tomorrow, right? In Google Meet. Okay, right.